So my name is Sanjay Kumar, and I'm the Vice President of Product Management and Marketing at Arrcus. Really excited to be here today along with my colleagues, both in person as well as the ones online. We're really excited to present to you an overview of our company as well as some exciting developments that we're doing in the area of building out networks for the AI world. So the course of this presentation, please feel free to engage with us. We're here so that we can get feedback from you and really get your insights as well. So let's just keep this interactive. And with that, we'll get on with the show. All right, so we have a packed agenda for today. My colleagues and I will walk you through quickly, what we do at Arrcus and introduce the ACE AI platform. That's the latest. That's the latest networking solution that we've come out with, and we'd like to talk to you about how we're using that to solve some really interesting problems and hard problems, really, in the world of AI today. After that, we'll talk a little bit about our automation capabilities and how it is that we enable operators to be able to really reduce their operational complexity as well as operational expenses. We'll then have a couple of demos. We have one exciting demo where we'll show you how we've been able to offload some key networking capabilities onto Bluefield 3 from NVIDIA. And then the last demo that we have is around our multi-cloud connectivity platform with egress cost control and how that can help operators lower their cost for egress from an egress cost standpoint when traversing from one cloud to the other. So that's what we have. And again, let's just keep this interactive. Okay, so I'd like to now kick this off, and I'll be joined with Keyur Patel, who's our CTO and co-founder as well. So let's talk about Arrcus as well as the new platform that we've introduced called ACE AI. Now, just to give you a quick overview of Arrcus, we are innovating and disrupting the networking space with a completely different approach to networking. We are essentially virtualizing networking by delivering you a very modular and modern network architecture that can run on any kind of hardware and absolutely anywhere in the network. When I say it can run on any kind of hardware, we of course run on merchant silicon-based white boxes from ODM vendors, and we support the range of Broadcom silicon, both the XGS as well as DNX. We also support Barefoot Tofino switches as well as NVIDIA Spectrum switches. But beyond just switches and routers, white box switches and routers built on merchant silicon, we also have the ability to run this on compute. So we run them as VMs, we run them as containers, for example, for edge type of deployments. And we've expanded that now to also include accelerators and SmartNICs. So we run on NVIDIA Bluefield 3, for example. We also run on Intel NetSec accelerators, which we'll talk about as well. And so what this does is this really expands and opens up the number of use cases that we can enable and the different places of the network that we can run the operating system. This also lends us to be able to operate in the core, at the edge, or in the cloud. We are fully certified across all of the different cloud vendors, so that's AWS, Azure, OCP, or GCP for that matter. We have a complete certification on all of those clouds, and that enables us to provide on-ramp to the cloud, connecting between the clouds as well as within the cloud. All right, so that's a quick overview. And in terms of the type of use cases that we enable, it goes all the way from the access through the aggregation layer into the core and into the multi-cloud. So you see this really, the flexibility of our platform enables all of these different use cases. And this opens up a variety of interesting use cases for customers. And speaking of customers, the kind of target customers that we have range from high-end financial services companies that deploy us in their data centers, or for that matter, we've got high-end retailers who do the same thing. We've got co-location providers who've deployed us in data centers, replacing their traditional networking vendors with our solution so that they can get much more modern networking stack. They can get much greater agility when it comes to innovation. They get much better total cost of ownership as well. And so apart from that, we also have we've got network operators or mobile operators that deploy our networking stack, and SoftBank Mobile is one of those that has deployed us to automate 5G network slicing and deliver more capabilities and services on top of that. So in sum, we address high-end enterprises, we address co-location providers, we address cloud operators, as well as service providers. Now, what we're going to talk to you about today, and just wanted to list this out up front rather than walk through everything. So this is one of those TLDRs. But the executive summary is we're going to talk to you about our ACE AI platform that really addresses the paradigm of distributed AI cloud, hybrid AI cloud, so to speak. And we address networking all the way from the edge to the data center into the multi-cloud. We'll talk about that. Training networks require very large scale networks, and we address that with two types of architectures, namely IP clos as well as virtualized distributed routing. For the edge compute, we are introducing a brand new way of networking so that inferencing applications can run on these edge compute devices. And then to tie this all together, we have our multi-cloud solution with egress cost control that actually helps you reduce the cost as you traverse for workloads from one cloud to the other. We deliver this through our network operating system that is microservices based, container based, and cloud native architecture. This supports a distributed CPU core and gives you much better performance, fastest convergence in the industry. We're completely hardware agnostic, as I mentioned, whether it's white boxes with merchant silicon or compute as a VM or container, or for that matter, running in the cloud. We are open config based, and so northbound, we enable a lot of different ways in which customers can integrate their own orchestration platforms or third-party applications straight onto our stack, and we are open config based, so we have Yang modeling, Ansible playbooks, and so on and so forth, which we'll also talk about. And we do this all by reducing the total cost of ownership, at the same time reducing the total cost of ownership and reducing power consumption. Our customers benefit by reducing their costs by about anywhere from 30 to 40%. So that's sort of your TLDR summary. Now, coming to distributed AI. Now, historically, and it seems odd to say historically because this has only happened in the last couple of years, but training models have largely been run in centralized locations with massive amounts of compute, lots of GPUs tied to lots of storage. And that's all happens typically in the public cloud. But now what we're finding is that customers are beginning to partition these learning models and run them in different locations. This gives them much more computational efficiency and also allows them to sort of right size for the type of applications or the training models that they might have. In addition to this, what we also see is that inferencing models are really becoming more and more important, and those are being run at the edge. As a result of all of this, what this essentially means is that you've got your AI workloads and training models or inferencing models completely distributed across the network between the on-prem as well as in the public cloud. And you have massive amounts of data that need to be shared between all of these different resources, and that helps optimize the models, right? So that's the sort of world that we now have and this hybrid AI cloud. And essentially what this means is that it is solving for, from a networking perspective, is no longer just limited to a silo of a data center, but it needs to address this entire distributed or hybrid AI cloud paradigm. And that's really where we're coming in from with our networking solution. If you take a look at what are really the demands and challenges for these workloads, I'm not going to spend too much time on this, but you see the difference between just the Llama models and the GPT-3 large models. The number of parameters that have to be trained all the way up to 175 billion. And what this essentially means is a massive number of GPUs, and this means an order of magnitude increase in the amount of data traffic that actually needs to be handled by the network. You can see that GPT-3 scales all the way up to 10,000 GPUs. Now, how do you bring all of these together? This also means, so apart from this amount of data transfer, what this also means is that now things like elephant flows become more pronounced. Things like low latency and your tail latency are problems that you need to start solving. You need to have lossless connectivity as well. So these are the kind of really demands being imposed, and sort of what leads us to what we're looking to deliver. With this, let me hand it over to my colleague Keyur Patel to walk us through the rest.
Thank you. I'll go back one slide, and there are a few interesting things worth noticing here. Number one, the models, the number of models that are coming out are growing exponentially year over year. You have hundreds of models. 2 years back, you had a handful of models. And these models are being trained even more as we speak, depending on what applications they target on. The very interesting thing here you see is between the GPT-3 and Llama models is that the number of tokens have significantly increased. And what that means for networking folks is that we love it. Why? Because the traffic's going to grow. And that is what it says that, as the models grow, as the tokens grow, as the number of GPUs grow, you're going to see more east-west traffic that's going to come for the fact that AI requires you to have a lot of east-west traffics to complete the workload. It's a distributed computing in some sense. Actually, it's the distributed computing. Now, if you look at the GPUs, they have significantly advanced as well. What they say as of current GPUs is that they are capable of actually ingesting 800 gigs per GPU. And this is where Ethernet becomes very interesting. Not only it's a mature technology, it's very well understood by data center folks. So you don't have to train them on Ethernet versus InfiniBand. InfiniBand is known to select few, but Ethernet's widely adopted. Quite ubiquitous. Back in the day, you had T1 events, frame relays, all sorts of networks. And therefore, when the packets traversed across networks, you would have to change the headers. Now, even if you do that in silicon, there is a cost that silicon incurs. Just as there is a cost where programmatic silicons incur versus low buffered, fast silicons like Tomahawks give you low latency, right? So it has great advantage as Ethernet is widely deployed. Higher scale. Back in the day, it was 10 megs. Now it's 800 gigs and beyond. So scaling out very nice, robust features. You have congestion management and QoS built upon it, which means you can do everything that you want in terms of shaping and managing the flows. And last but not the least, it's extremely cost effective compared to InfiniBand. So when you deploy Ethernet into data centers for AI, one thing to keep in mind is Ethernet was always loss. Loss of packets were assumed inside Ethernet. It wasn't lossless to begin with. Now, when we look at AI, we aren't looking at packet delay across each hops as the packet traverses through the hops. We are looking at a flow delay end to end, which means from one GPU to another GPU, how long does it take? And longer the delay, longer the time it takes for you to converge from a workloads perspective. This is called the tail latency. So it's extremely important that you get the tail latency down. And this is because when you look at the compute workflows in data centers, the compute cores were cheaper compared to the GPUs, which are very expensive. So you want to recoup the money, want to get back your investment, you want to have the workloads complete as fast as possible. So tail latency matters. What causes the tail latency? Well, a number of things causes it when you look at network flow. You could have flows colliding with each other, as Sanjay was talking about. You could have elephant flows, and that requires you to shape those flows through the network so that other flows get enough bandwidth to go through. Or you could have, just sub-optimized ECMP, or you could have packet drops. So it's important to sort of solve these problems when you start looking at Ethernet, because some of these things are already handled by InfiniBand very nicely. Now, this is where UEC comes in. When you start to look at UEC, what they are trying to do is improve Ethernet in areas where it can come up to the parity of InfiniBand, whether that is taking care of multipathing and packet spraying, or you are doing flexible but high-end telemetry, or you're doing some sort of scale, or it could be congestion control. How do you do efficiently end-to-end by signaling the flows? We have been working with them very closely, and one of the things we want to do as the standards develop, we want to productize them. Whether that is through the use of silicons that can come up with certain capabilities, or software that can fuse with silicon and build those products, whether they are switches or routers, that can get you end-to-end performance. Essentially bring Ethernet closer to InfiniBand and better as the speeds and feeds grow. So coming back to those tail latencies, if you were going to solve them, in other words, what do you need to do when you start to look at Ethernet AI-driven networks? Well, you want high performance. More importantly, as Sanjay was talking about, you want lossless connectivity as well. You want latency to reduce, but you want that to be extremely predictable so that the tail latency comes down. High availability, zero impact failover, which is a new term. Back in the days for the routing, they used to call us TILFA fast convergence of 50 milliseconds and below. Here you're talking about nanoseconds. So some of the functions that we used to do with control plane in combination of hardware has to move to hardware in order to get that going. And last but not the least, you want to have visibility so that you know what's happening in the network in context of flows and how you tune them better off, yeah? Now that you look at these problems, what it drills down in context of AI networks is the fabric. You want to build a fabric which is seamless, as we talked about, less transitions, therefore the silicons are as fast as possible. Whether that is Ethernet, de facto at layer 2, and do IP, MPLS, EVPN, or segment routing if you're looking at flow-based traffic manipulation. You want that built inside the fabric. High availability is going to be super important here because you don't want packets to be dropped. That means less node failures. If you're going to pull a switch out or a router out or a compute out, you want to do that in a very graceful manner. You want to do it in a manner that takes least amount of time. And you want to support all the fast convergence improvements that are there. Either silicon supports it, how do you build on top of silicon to signal the failures end to end, so forth and so on. Then you want to do flow handling, whether it's through ECN, PFC, how do you shape, how do you figure out what is congested, where it is, and how do you tune the congestion? That becomes very important. Of course, control plane is going to be super important if your GPUs are going to grow in tens of thousands. How do you make sure the reachability is reached everywhere in a scalable manner, in a distributed fashion? And last but not the least, as we talked about, control plane as well as hardware-based streaming telemetry, so you understand what's happening at the packet level, flow level, and what is the control plane doing. Is it in alignment? Is it out of alignment? Where are the failures? So forth and so on, right? So fabric becomes very important, and this is where we think software kicks in combination of hardware. Here is a good overview. I think we've presented to you in past, but this is what we do from an architecture perspective. As Sanjay said, this is a microservices architecture, has all the components in user space, fully restartable. Notice we have up here data store that is designed to scale out and do telemetry, collect the ephemeral state and stream it out. Whether you use GNMI, gRPC, Kafka is the choice of the operators, but you can stream entire control plane telemetry out not just the counters. Then you have protocol stack, and here is the layer where we abstract silicons. So one of the things you want to do as part of the fabric is enable newer silicons, different kinds of silicons, in a manner that it becomes seamless across the network. So this is a great overview of what we're doing. Now, as Sanjay was talking about, if you see Ethernet as a fabric, which is what we see, you see fabric on top of that that requires Ethernet or sort of makes Ethernet lossless with the features that we talked about in combination of hardware and software, then what are the places where AI would be applicable? And as Sanjay had shown the earlier diagram where we span across from edge to core, why is that in context of AI? So again, we think from training perspective, the training models will be in cloud, or they may be in data center, or they may be hybrid, and that you may need a connectivity between them. Inferencing, definitely it's going to be at edge, and there are various flavors of edge that are showing up, and we'll talk about that. And obviously, all three of them are glued with high visibility and automation so that you can tune the traffic across these different domains. Yeah. Over to you, Sanjay.
Thank you. Thanks so much, Kayur. So just to recap, and I'll just go back to this slide again, just to recap. So what we're saying is that you need the next generation of networking within the data center. It needs to support massive scale, massive amounts of data. It needs to be lossless. It needs to be congestion free. That's number one. Number two, for inferencing, you need a brand new way of networking at the edge. So that's the second thing. The third thing that we're saying is you have data being transferred in this distributed AI model between the different locations, wherever those workloads may reside. And in order to seamlessly access all of those different elements, you need hybrid and multi-cloud connectivity as almost like a fabric. And then the fourth pillar over here is the fact that you need visibility and the ability to automate so that you reduce the complexity of your operations. So that's really, those are the sort of the key pillars of what we've introduced as part of ACE AI. So coming to ACE AI, therefore, we've got our operating system that resides on all of these different form factors, different types of hardware. We have the ability to scale up and scale out, so therefore deliver much better performance, much faster convergence times in the industry as well. We support multiple underlay and overlay options. That gives you the flexibility to be able to deploy this both from a data plane standpoint as well as a control plane standpoint, build that fabric out. And of course, we'll show you the choices of silicon that we have that take you all the way to 800 gig and beyond. And then the automation capabilities as well as the multi-cloud capabilities. So jumping into these one by one. So let's talk about how we're solving for training within the data center. So traditionally, what you have on the left-hand side is you've got an AI network based on InfiniBand to connect all of the GPUs as well as the storage attached to that. And then you have, you've got your Ethernet Ethernet fabric that is kind of at the back end. This paradigm essentially means that you've got two different networks that have to be managed. If you look on the right-hand side, that's what we're proposing is a unified architecture that Arrcus delivers, which is Ethernet-based, and that completely unifies, gives you this new type of architecture for your training workloads and connecting all of those GPUs at scale, and at the same time, using the same architecture to address the back end of the data center as well. So this gives you much greater efficiency.
Yeah, yes. Sorry, this is Remington, just to clarify there. So you said unified. In the picture, it looks like it's actually a separate physical network. Are you saying that it's simpler to draw that way? So I'm not in any way complaining about the depiction. I just wanted to make sure that I understood, though, that the top diagram, which has the spine leaf topology there, is the same spine leaf topology that you have at the bottom on the right side.
That's correct. Okay. That is correct. But the one at the bottom are really dedicated to connecting all of the GPUs and therefore the storage as well.
Gotcha. Okay.
Yeah.
Quick question on the logos.
Yes.
Are you working with Oracle Cloud at this juncture?
Yeah, so definitely OCI is one of the clouds that we are certified with, and we actually do multi-cloud connectivity for that. All right, so within this data center, we have two distinct architectures available, right? Depending on, and we'll talk about what kind of characteristics each one of these architectures have, and then therefore there's a choice that a customer makes in terms of which one they want to choose. So we have an IP class architecture, which is your leaf spine, super spine, however many tiers you might have. And then we also have a distributed fabric or a distributed routing architecture, wherein with sort of breaking open the chassis-based, typical modular chassis-based architecture, this enables scale and a pay-as-you-grow kind of a model. So this, if you're looking to scale across a massive number of GPUs, this sort of an architecture comes in very handy. What we do over here is we have solved the problem of disaggregating the data plane from the control plane so that you can run your data plane on the boxes and keep scaling as you go along. So this is a very innovative architecture that solves a problem over here for AI networking, especially when it comes to massive number of GPUs. Some key tenets of what we're delivering over here. High performance and lossless connectivity. So, with features like Rocky V2, which enables priority flow control to proactively deal with any kind of packet drops and create those thresholds, or reactively with ECN. So this takes care of your flow control. And then we've got features which enable load balancing, and that is with the ability like things like cognitive routing, adaptive routing, dynamic load balancing, global load balancing. And these help you essentially better utilize or optimize your entire resources and be able to extract much more from the network. All of this helps deliver lower latency and reduces the job completion time. And that is extremely important. You have all these GPUs, super expensive. You want to make sure that the network is not holding up the operations. And that's what this combination of performance, the lossless connectivity, the flow control, as well as congestion management and load balancing help you with. At the same time, we deliver very high availability features. So we've got seamless failover capabilities. We've got the ability to do hitless upgrades as well as graceful restarts, as Keyur was mentioning, so that once again, this gives you a much better utilization from your GPU perspective. Let me pause here and see if you have any questions. We're going to go into each one of these.
I just have a point of clarification.
Sure.
I'm not sure I heard correctly. So when Remington asked about the slide a couple ago and whether or not you were talking about a converged front-end, back-end network, or whether or not it was two different networks, we are talking about basically a converged front-end and back-end.
Yeah, and I'm going to ask Keyur to jump in on this as well. So it depends on how the customer is building that out. It could be a converged network. It could be two distinct networks. But I'm going to ask Keyur to also jump in and clarify.
Sure. So it could be converged. It could be two different networks. What's the key is, going back to the question you asked, is you're going to see the architecture of class being as is. Compute nodes have different characteristics in sense that it may be 100 gig, 400 gig leaf spine network. You could have drops in those networks. They are assumed that the packet drops would be there. In AI networks, you're going to turn around and absolutely make sure in this design, it's going to be lossless, more importantly, predictable latency across from end to end. So that's the big difference. Whether you combine the networks or keep them separate is going to be the flavor of the day from operator's perspective. But a solution has to adapt to both is the key. Yeah.
Okay. So with that, I'm going to hand it to Keyur to talk to us through both IP class as well as our distributed routing.
Can I interrupt for just a second before you do that?
Sure.
If you go back just one slide, please. Sorry, this is Remington. You have on there a packet spraying across the backplane for optimal load balancing.
Yes.
Are you doing something special?
We'll talk about that.
Okay.
We'll talk about that's the
Great
key.
question.
Yeah.
And that's a great question.
Thank you.
So some of this feature list that we talked about, I'm not going to rehash this, but suffice to say, we are actively working on this. We are actively working on ROC V2, Rocky V2, RDMA over converged Ethernet. DCQCN is something we'll be looking at, PFC, ECN. or adaptive routing. Adaptive routing is more in the hardware that is very analogous to, at a very high level, overly simplified, BFD implemented in hardware, where you can do everything from figuring it out that the link is congested to the fact that link may go down and that you need to adapt if the ECMP is in there. How do you sort of do that at a hardware level at the nanoseconds? But more importantly, what is going to be the key is how do you sort of tune the software to unleash this feature at scale within the network that we've been talking about. This is a quick reminder of what RDMA over Ethernet is. And, suffice to say that this has been implemented for a while. People know about it. People have implemented in HPC as well as storage clusters. The big benefit of this in compute world was that you bypass the host stack. And in doing that, it gives you the latency benefits that you would otherwise not incur. And therefore, running it over Ethernet gives you all the benefits that you would have on Ethernet. Well, this applies seamlessly to AI. And that if you do this right, some of the characteristics that we want in Ethernet for AI networks are realized. So this is another area that we look into. You asked about, are we doing something special? That brings us to virtualized distributed fabric. This is very interesting. As Sanjay talked about, this, in other words, disaggregates the chassis today in the router market. But even in the router market, there is a concept where here we have a front panel ports, which is 100/400 gigs right here. And this is the backend, which is the fabric card. And this is typically hidden. This part of the network is hidden in chassis. This is where your control plane resides. And these are the PCIe or advanced Ethernet switches that connects your fabric cards as well as line cards with the RP. Now, this is all opened up, what we call as a virtualized distributed cluster. One interesting thing about the backplanes is that they don't do packet-based forwarding. They do cell-based switching. And that allows you to evenly spray packets across all the links. And that's a one big benefit because you don't want the flows to collide over each other. And the great way to do that is you spread them across and then you rebuild the packets at the very edge on the egress point. A big benefit of this is, as we were talking about, it gives you somewhat closer to perfect load balancing that we've been talking about, that you want to realize at cell-based. This is actually one of the things that InfiniBand does it very well, in sense that it doesn't do flow-based hashing, but it does a packet-based spraying across ECMP links. Obviously, this is congestion-free because all sorts of congestion notification or application that you want to do happens at ingress and just at egress. So everything in the core is something that you don't worry about, and therefore there is no hop-by-hop TE or congestion that is needed. Now, this is built with deep packet buffers, which is routers. So obviously there is a cost associated to it. More importantly, this can be collapsed. The layer 2 and 3 up here can be collapsed. So this would be a two-stage clause, which is phenomenal because it gives you upper bound on the latency that we talked about. And last but not the least, the chipset, as I was talking about, it gives you ability to reconverge in nanoseconds, and therefore you want to hit that zero impact failover that I was talking about in hardware itself here, knowing that there is an ECMP that's going on, right? So two different designs, as Sanjay talked about. You can build the networks with switches. If you build the networks with switches, there is no cell-based fabrics at the higher layers. And what it means is you need to do some sort of PFC, ECN, figure out load balancing, and figure out that any congestion is in there, you want to signal it, apply tuning to the flows, whatnot, hop by hop. These fabrics are somewhat limited in our opinion. So anytime you want to have something as a network with 2K less, 2000 GPUs or less, you could think about switch-based fabrics. But if you have networks that are going to scale beyond 2000 GPUs, definitely want to look at flattened architecture with deep packet buffers that we've been talking about. Does that answer the question you were looking for?
Yes.
Super.
Thank you.
I'm going to quickly switch over to inferencing. We've talked about training. We've talked about what does it take to build the networks and how are we applying that. We have so far enabled everything from 1 gig to 400 gigs on switching side, as well as 1 gig to 400 gigs and 800 gigs on switch and our routing side. So you see how that was applicable in the slides before. Yes, please.
Yeah, hi, Micheline Murphy. I have a question about your deep packet buffer. That's a hardware solution to a, to a congestion problem. How does your solution address that in a software? Is it doing some kind of fabric scheduling in order to be able to optimize the packet, the buffering in the packet?
Fabric scheduling, configuring that, tuning that, getting a feedback loop. A lot of times the problems are that you configure something, but you have no idea about whether that is being applicable or used or is been working as you want. So there is this feedback loop that we also work. And we work that in conjunction with software protocols that run on top of it to say, here is how we build the fabric. Here are the ECMPs. If the ECMPs are present, you have high availability in place. If the ECMPs are not present, you have to worry about high availability. So all those things, software will take care of it on top of what hardware provides. But the key point is you got a solution that has to come with hardware plus software that holistically attacks that space.
So yes, you
Yes.
have scheduling. Okay,
Yes.
thank you.
Thank you. Any more questions? Let's go to inferencing now. So inferencing is faster but less resource intensive. That pretty much applies at the edge. Now, like I told you earlier, we are seeing different use cases come up on edge. One of the interesting use case is in context of AI RAN. This is in 5G context. And what AI RAN does is it's basically fusing AI into cellular technology to optimize RAN networks. Now, this becomes very interesting for folks like us because, as Sanjay had mentioned earlier, we do SRv6 with mobile user plane where we have optimized 5G networks in a way that we have pushed IP at the very edge. It allows us to now deploy things like AI RAN, which lets operators monetize the entire 5G. 5G has a promise of bigger bandwidth at the edge. Putting inferencing at the edge allows you to deploy newer services. They could be purely new services that operators want enterprises as well as the customers to use, and they could be a enterprise specific service, or it could be an infrastructure specific service where you collect the data from RAN, use it to fuel the AI and tune it for the RAN networks itself so as to give better enterprise connectivity and service offering, right? So this is one area that we see coming up very nicely, and it's a low-hanging fruit for operators to go in and say, how do we tune this and how do we monetize it? Here is the depiction. Yeah, please.
Quick question. Also, this would align with 5G Advanced,
Yes.
release 18. Okay.
And 6G.
So we
And
have to wait until 6G
Yeah,
for this
yeah.
to really
Yes.
coming home. Okay.
Yes.
I just wanted to see that. That was part of the timeline roadmap.
For
Good to
sure.
know.
Yes, yes. And here is a great way to look at that. You have an edge compute stack, typically consists of computes. Computes could have CPUs, could have GPUs, and definitely will have smarter NICs, which can do hundreds, 400 and beyond, depending on what the requirements of that edge, micro edge looks like. And you will have TORs. And what you will need is to build a fabric, which could be an underlay, and then a fabric that could be an overlay, depending on what you need. So what we are doing, again, is looking at this compute, relegating networking right on the DPUs and IPUs that we talked about, putting all the complexity of whether you want underlay as well as overlay, all the requirements at the IPU or DPU, and then let the compute do what it is required for. The TORs will do some more smartness if it's required there, It could be deep packet buffer or shallow packet buffer. But this is how we see edge compute market evolve. And as it evolves, it will have multiple different applicabilities depending on the verticals. In any case, you will need a network, and that is what we target for. Yeah? Any questions?
I have a question.
Yes, please.
So I'm sure the tech is great, but there's a lot of people who do what you just said. So help me understand, if I'm a customer, why am I choosing you? What are you guys doing that's unique or different about building that AI network? Like, can you give me the 2-sentence answer about why Arrcus over any of the other major OEMs out there that are going to help me build a Clo fabric for AI processing?
I can take a stab and hand it off to Sanjay, who's going to take the next section as well. But 2-sentence answer: automated fabrics, scalable fabrics, ability to smartly deploy it at the edge, relegate networking to the DPUs and IPUs. And for the fact that software has shown adaptability to unleash different silicons at scale, as Sanjay was talking about earlier, it just puts us in the forefront of the technology that not a lot of other vendors have shown to do, or they have done it with different sets of software.
Is that because of execution?
Both execution, solid design, and very solid architecture, because it goes back to architecture that translates into software that translates into the deployment. Yeah.
Okay.
Over to you, Sanjay.
Thank you. Yeah, and the only thing I'll add to that is that it's the only software in the industry that offers you a unified approach to very many different problems.
Because you're addressing both edge and data center,
as well as the ability to seamlessly pull all these together. You'll have solutions for the data center. You'll have solutions at the edge. You'll have solutions for multi-cloud networking. We're the only ones that give you the flexibility to bring all of this together and seamlessly access all of these AI workloads wherever they may reside.
So why do you think you guys can do that and other people are struggling? What is it that you're doing that's different?
Great question. So I think number one, ground up the design from an operating system perspective, building that flexibility that is completely future-proof and unleashes all of these new applications. The number two is this particular operating system, the way it was designed, also to very flexibly reside on any kind of form factor. So it's really this ground up design that it has enabled, and the vision that Keyur and the other founders had in bringing this to the market, recognizing that you need an operating system that is going to be able to maximize the innovations that are happening from a hardware perspective, right? And if you have a vertically integrated strategy, that's going to take much longer. So I think that's really where we come in, and we stand above the others, is what we believe.
Thank you.
Thank you. Okay, so what are the platforms that we have introduced in order to be able to address what we talked about from a training and inferencing perspective? So we support Broadcom Silicon with the next generation of AI platforms, that's Tomahawk and Tomahawk 4 and 5. And at the same time, on the distributed routing front, where you spray across the backplane, as Keyur was mentioning, we've got Jericho 3 and Jericho 3 AI. Those are the line cards, so to speak. And then Ramon 3 is the next generation that addresses the back fabric and the backplane. So we've got that. We also support NVIDIA Spectrum switches, and we support NVIDIA Bluefield 3. Bluefield 3 is very exciting when it comes to all the inferencing kind of use cases it opens up, which we'll be showing you as well in a few minutes. Digging down deeper into the kind of platforms that we have enabled, so we've got platforms from UFI Space and EdgeCore for both for the Tomahawk 5 and Tomahawk 4, and we've got NVIDIA Spectrum 4 as well, Spectrum 3 and Spectrum 4. This gives you massive capacity of 64 ports of 800 gig. And really, this is really the next level of silicon. And this is one of the reasons why we can do it faster than anybody else. We have a much quicker way of being able to onboard, because of our abstraction layer, any kind of merchant silicon. On the VDR front, I talked about this, but this is Jericho series is now Jericho 3 and Jericho 3 AI, as well as Ramon going to Ramon 3. And within this, they have the proprietary technology of being able to spray across the backplane and then be able to reassemble. Sorry, go ahead. You have a question there.
So that you're leveraging what?
We're leveraging the
Jericho 3 AI
Jericho 3 AI.
for the spray, because they
For
did the
the
presentation. Was it last Network Field Day or the one before? I can't remember, but
The Tomahawk.
they presented on the Jericho 3 AI
Yeah,
chipset.
that's right.
If folks are interested in that one, go check that out. That presentation. So you're leveraging that with.
That's correct.
Okay.
That's correct. So we build on top of that.
All right.
Just going to keep moving. Okay, so now this is the interesting one. So what we find is at the edge, specifically for the inferencing use cases, there's a new way of networking which essentially provides you with a converged compute and networking type of a device. What this means is there's much greater power efficiency. It helps save a lot of costs, and at the same time, it also frees up your CPU from doing any kind of networking capabilities. Now, with this SmartNIC or the accelerator card that goes into a server as a blade, you can offload networking. And we're finding a lot customers coming in with a lot of requests which center around either security. So let's say IPsec or MACsec at very, very high throughput. That could be within the data center, or it could be at the edge, in fact, trying to connect to the clouds, for example, or connecting to other locations. SRv6 being terminated on the SmartNIC itself, being terminated at the server to enable traffic engineering. We've got network slicing, which is the demo we'll be showing you today of how we've used SRv6 along with mobile user plane to be able to deliver and automate network slicing right to the edge. And that enables a lot of different use cases. Offloading the entire routing stack onto SmartNIC itself is another use case that customers are talking to us about. Again, that's in the interest of having a converged platform that is much more power efficient. Multi-cloud networking along with security, like a virtual router sitting over there, connecting you, ramping you to the cloud or within the cloud across clouds as well.
Just a
Yes,
quick question. Are you saying that the software runs on these devices or on the host that these devices are plugged in?
Great question. So we run it on these devices, on these accelerators, call them a super NIC, call them a DPU, call them accelerator, depending on which vendor it is. But we're terminating our networking stack on these itself, leaving the CPU completely free from having to do anything regarding to networking. So it's a complete offload.
So for edge networking, it's a really interesting use case to have a single NOS for the entire platform for all the routing, switching, NFV. How do you position that in the market for, is it positioned for financial services? Is it positioned for streaming media? Where do you think the target is to use this?
Yeah, that's a great question, Michael. So these are different verticals that we're seeing a lot of interest in. Financial services for sure, especially when it comes to security. We're seeing co-location providers showing a lot of interest when it comes to multi-cloud networking along with security. Mobile operators are looking at network slicing being terminated on these smart NICs to be able to get much higher and better performance. And so those are some of the verticals or specific segments where we're seeing interest around SmartNIC capabilities for edge.
So you mentioned security
Yeah.
in the slide, and you said it in your answer, but I don't recall, and forgive me, any of the features that you listed earlier, talking about things like um, intrusion detection or next-gen firewall or encrypt, decrypt, or IPsec. So are those features and functions also built into the Arrcus OS, or is that some sidecar type of application?
No, great question. So we absolutely support IPsec, the sort of baseline. So IPsec and MACsec, these are the capabilities that we have on on these smart NICs today. And then, of course, the roadmap of this evolves to things like firewall capabilities, and so on and so forth. Does that address your question, Michael?
Yeah, interested in what the security functions you're developing aside from IPsec and MACsec might be. Line rate IPsec on the DPU is certainly something that's very attractive.
Yeah.
Especially as we move into the encrypt everything everywhere mindset. But also interested in understanding what security functions you're bolting into.
Yeah, absolutely. In fact, we'll be touching on the performance throughput, and definitely happy to follow this up as well. Okay, I think we can breeze through these in the interest of time.
One other thing that we support, obviously this goes without saying, Michael, is IPsec alongside with TLS. Offload is also something that Bluefields do very efficiently. So that's another area to look into. How do we do this? As I told you earlier, that we have unleashed all sorts of silicons. By that comparison, we've managed to run the operating systems on top of ARM processors, and that allows us to relegate an entire networking stack to the DPUs or IPUs. Now, this allows us to do other interesting things inside of security over and above the advantages that we have listed here. Is that when you think about router pipeline, you think about things like DOS, you think about things like COP to protect your control plane policing. So those are the kinds of things we will target first to tweak the pipelines to say, how do you get there? And therefore, if you do cloud-based networking, either AI or a data center networking for AI, one good way of protecting the workloads is what is known today through COP, IPsec, or all sorts of ACLs like policy. So these are the areas where we are super focused on, because these are things we have very nicely enabled it for the router silicons. Yeah. Any questions here before I turn it off to Sanjay? Super, thanks.
So in fact, the demo that we will be showing you around Bluefield 3 that we enabled, this was in conjunction with NVIDIA at the GTC conference that we had done this demonstration. So we will get to that very soon. So now we talked about training, we talked about inferencing, now multi-cloud networking, and how it all helps tie this together with a cool feature that we have called egress cost control. So that's what I'm going to jump into. Go through some of these. We've already talked about the fact that these are workloads need to be seamlessly stitched together. So what we have with our solution is the ability to, and again, to the earlier question of what differentiates us, again, unified software that delivers this capability. You can run it as a virtual router to enable ramp to the cloud from your on-prem. You can use it to connect between the different clouds as well as within the regions of any cloud across Azure, AWS, GCP, and OCI. Right. So this is what we do.
Can I interrupt for just a second? So
Sure.
We saw before your ability to run on any platform, which is very cool. But when you're running it in cloud, or you're running it just as a pure software function where you don't have control on the physical environment, is it going to leverage functions from DPDK or some other capabilities to get some of the hardware acceleration from the public cloud providers?
Yeah, great question. So what we leverage things like VPP to enhance the performance where it's required, and then to definitely blaze through that, things like the DPUs will help over there as well. Okay. All right. So now, if you take a look at these data transfers that we were talking about, the ones that are not latency sensitive, right, where you're running some training models and partitioning them across different places, you've got inferencing, interacting with training models, these latency insensitive flows or data transfers can get really expensive, right? So, and this gets to the heart of what is a barrier as far as multi-cloud connectivity is concerned, or multi-cloud networking is concerned. There is an egress cost every time you exit any particular cloud vendor. And those costs are hidden and they can grow. and it usually comes as a sticker shock. It's estimated to be anywhere between 15 to 20% of the overall cloud bill of any enterprise. So this is a real problem. Now, what we are doing to address this particular thing is introducing something called egress cost control. Egress cost control is a very intelligent methodology that we've built in, with, and this is patented. What we do is we are able to take a look at all the different underlay options available, whether it's a private link, whether it's the internet, or whether it's interregion or direct connections, whatever that might be. We take all of those costs into account and at any point of time dynamically route the traffic to those egress points that reduce the overall egress cost. So the way we think about this is almost like booking on kayak travel, for example. You go from San Jose to Tokyo, take a non-stop, it's probably going to be the most expensive, gets you there really quickly. But if you have time on your side, you can look for options that give you different hops, perhaps, takes longer, but reduces the cost. Simply speaking, that's what we're doing with egress cost control. And this is a really intelligent technology that we've introduced. We'll do a demo on that as well.
So you're saying egress costs are still persisting despite some of the recent announcements that say they're dialing it back?
Great question. So the recent announcements had more to do about if you were exiting any particular cloud vendor, you took all your data with you, they said, fine, we'll enable that migration without charging you. But on an ongoing basis, when you traverse between clouds, you get hit with that egress charge. It's almost like a toll.
Right on.
Can you clarify, excuse me, this is Remington again. Can you clarify how you're gathering the cost data in real time to make that decision?
Yeah, great question. So we have APIs that go and poll the publicly available information. At the same time, if you have private links and you've got certain costs negotiated, you can upload those into the system as well. And so we're constantly taking a look at what's going on. In fact, even volume tiers, volume-based tiers and different pricing, we take that into account as well.
Okay, I guess the hurdle that I'm having there, just a little bit understanding, is if you're calculating on volume, how do you know how much volume is going to be in the flow before the flow starts?
Well, what you know is what volume has been hit thus far.
Okay.
And you know the size of what's going to be sent out, so it sort of makes an approximation.
I got you. And then when you say you go out and pull APIs, if you had a negotiated lower cost associated with it, are you pulling it from, say, my dashboard in the cloud, or are you pulling
you can
data?
Upload that information.
Okay.
So private links, negotiated costs, whatever that might be. Okay. You may have a co-location provider, a middle mile,
sure,
that you've negotiated some prices with. You can upload all of that. You had a question.
This is Micheline Murphy. I just wanted to make sure we're talking about dollars now. We're not talking about congestion, or just so that I put a stop in the conversation we just had about AI and low latency and
these are
performance.
dollars.
We are talking simply about dollars.
Correct.
Okay.
Dollars incurred when you exit any particular cloud.
Okay. Follow-up question.
Yeah.
If I was made of money and I didn't care about the dollars, but I wanted my data to come down fast.
Yeah.
Is that something that you have?
You don't have to turn this on.
Okay.
You don't have to turn this on. Typically, what will happen is BGP will take the shortest path available, the quickest path available, so you're going to get there.
Okay.
So this is for traffic that's not latency sensitive.
Gotcha.
Right.